welcome you to my lecture today. Of course, today we're going to focus on transformation. Give me 1 second. I'm going to upload that now. Give me 1 second. Those of you online, I need someone to talk. If you can see my screen, like what I just uploaded, can you see that? Those of you online.
Yep.
Yeah, I can see it.
Okay, thank you so much for confirming that. So I want to welcome you once again to this topic that we call power transformation. Okay, so the outline, we're going to have just like what I used to do. I'm going to have a recap on what we've done before because topics in statistics are connected. And I think I'm going to have a review of the previous section. And from there, I'm going to walk you through what we call transformation of linear regression. Okay, so let me first start reviewing what we've done before. You know, the problem is just like we want to characterize relationship between two variables. And why do we want to do that? We want to do that because using the relationship we can make a prediction of one variable based on the information on the other variable. And because of that, we're going to start the process by specifying model. Okay, so we specify linear regression model. And of course, the reason why we specify linear regression model is because we first generate a scatter plots, and from the scatter plots we got a sense of linearity like a straight line, and that was why we specify the linear regression model in the first place. Now, specifying linear regression model using the method of ordinary least squared, we estimate parameters in the linear regression model, the beta naught and the beta 1. And after doing that, before we can use the model to, you know, maybe make a judgment or inference, we need to first subject the model to diagnostic testing. And by diagnostic testing, it's more or less like we are revisiting assumptions underlying the use of the linear regression model. And of course, these assumptions are linearity, normality, constant variance, independence assumption, and the absence of unusual observations that I'm actually going to call outlier or high leverage. And of course, you know, if everything is good, like if all assumption hold, then the next thing we can do is, we can begin to make an inference, make a judgment, and whatever recommendation that we make using the model, of course we are not going to mislead. But what if in a situation uh, where the assumptions or any of the assumption is violated? If any of the assumption is violated, it means we cannot trust that model and we need to fix it. So what we want to do today is fixing a problem, like fixing when assumption is violated. Okay, how do we fix the problem? So today's topic actually revolve around what I'm going to call intervention. Okay, so because of that, so which means the variables, whenever there's a problem like that, a problem of assumption violation, then it means the variables in the regression model need to be transformed. Okay, and that was why I'm actually starting with the variable transformation. Okay, it's just like a child that is misbehaving. What are we going to do? We're going to look for a way to transform the child so that the child can start behaving well. Okay, so in a variable transformation, we can actually have what we call a linear transformation. For instance, we got a variable W, and this variable is problematic because whenever there's a problem in a model, what it's trying to tell us is that the variable is not in good statistical standing. So that variable needs to be transformed. And in this case, let's say W is a variable that needs to be transformed. If I want to go by transformation, I can multiply the variable by a constant. I can add a constant to the variable. When I'm doing that, I'm actually doing what I call a linear transformation. That's an example of a linear transformation. Another transformation we can think about is, considering what I call a power transformation. Because let me tell you what, linear transformation may not do the job. We have a way to test. We have to way to check whether a particular intervention is working or not. Okay, so another form of transformation is what we call power transformation. I can decide to raise the variable to power 2. Maybe because in the scalar plot, I'm seeing something that has to do with a curve and not a straight line. Of course, in your high school, you've heard about quadratic equation, okay, where you're going to notice a curve. I can raise it to power 3, okay, and so on like that. I can try different kinds of transformation that could, because when you want to fix a problem, you look for different ways, right, to fix a problem, right? You basically want to see the one that is going to work at the end of the day. Other transformation we can think about. We can talk about the trigonometric, like taking the sine of W. We can, if at times, it could be more than one variable that need to be transformed. For instance, I have a W1 and W2. Maybe by transforming them, we can just look at the ratio. I know in economics, you're going to hear something about index. Instead of me to look at the effects of experience on the salary of professional workers, instead of experience, I can talk about work history index. The work history index could replace experience. So if you take a look at what I have, okay, I can do a ratio, so like that. Like I said, we got different type of transformation. Now, there's something I want to show you now. W is the one that has a problem. It's a variable that has a problem. And we want to solve the problem by raising it to a power of a lambda, where lambda here is not equal to 0. Of course, when lambda equal to 1, you know what that means, right? When lambda equal to 1, it means you are still talking about the original variable. So we now want to figure out what is the appropriate value of the lambda for the relationship we are seeking between variables. And when lambda equal to 0, that is trying to tell us take the log. At times, taking the logarithm of a variable could actually fix the problem. But you know what I want to do now? I basically want to walk you through different kinds of values of lambda that may work. I wanted to take a look at that. I want to go from -1 to 2. We're going to try like how does the graphical representation of that look like when lambda equal to -1, when lambda equal to, now I'm actually going to plot that, and I want you to see. Okay, now I'm going to start with this. When lambda equal to 1, there's no problem, right? That is expected to give a straight line, right? Is that not what we're looking for? When lambda equal to 1, lambda equal to 1 means I don't need any transformation. That is what it means. There's no problem to fix. When lambda equal to 2, it's going to be a curve like that. When lambda equal to -1, that is what it's going to show. When lambda equal to 0.5, when lambda equal to 0, don't forget, when lambda equal to 0.5, that's a square root transformation. Square root. That is w raised to the power half. The w raised to the power 0.5. And when lambda equal to 0, if you see the green one, that's a logarithmic transformation. Logarithmic transformation. So these are the different kinds of transformation that we have, okay, that we basically need to identify whenever there's a problem, we want to face a problem, okay, we basically need to investigate what is the values of lambda that is going to work for our relationship. Now, the question now, why transforming the variables? Why can't we leave them alone? Why do we need to transform them? Of course, that was why I said, why not? Just because a variable is given you that answer doesn't mean that it is appropriate. Let me tell you this. Before you can make a sense of a module, don't forget a module contain variables. That the variables need to be in a very good statistical standing. I'm going to say that again. Before you can actually analyze our model using statistical technique, okay, you got to make sure that the variables you have in the model are in a very good statistical standing. And that was why I said, just because you have a variable in the data set doesn't mean it's appropriate. Because at times, most of the time, sometimes variable could be misspecified. Now, I'm going to use this example. The study of a country's economic development on child mortality rates. What are the important variables that I need here? I need the child mortality rate, the GDP, and the population. But the question is going to be, what kind of GDP am I going to use? Is it going to be GDP per capita or the different kind of GDP? Okay, and that was why I said, what are we going to do here? We're actually going to consider the dependent variable will be child mortality rate, but the independent variable will be a ratio of GDP to the population. What are we using here? This is an example of W1 divided by W2. Do you remember the other time when I started? I'm going to show you now. When I said, when we take a look at that, W1 divided by W2, okay? So that's an example. So this time, when you want to measure, child mortality rate, okay, you have a GDP, you have a population, for you to be able to put that in an appropriate statistical standing, you basically need to use GDP divided by the population. Does that make sense now? Okay. Another reason why we transform the variable. Like I just gave you one reason now, transforming a variable. One reason is to make sure the variables are in a very good statistical standing, because when you specify your model, the fact that you specify that does not mean the variables are well specified. Okay, now another reason why we transform variable is fixing assumption violations. Of course, now you know how, assumption that underline the use of linear regression model. Now the question now is, what kind of transformation techniques that work? Okay, I walk you through. There's a linear transformation. There is power transformation and so on like that. Okay, I'm going to take you into an example now where we basically want to model salary from years of experience for professional workers. Now, when you take a look at this, of course, you're basically going to start with a scalar plot, right? When you are studying relationship, don't forget that. That's a part of the preliminary investigation. What can you see? Does that look like a straight line? No, that's looking like a curve, right? Okay, so I'm actually plotting salary against experience. Okay, but let me tell you this. What if we do a linear transformation on experience? Don't forget, the linear transformation is it's not going to change situation, but if you want to, the essence of using a linear transformation is just to make sure the variables are in very good statistical standing. Maybe I should walk you back into what we mean by I'm going to show you once again the linear transformation that I just talked about. Now take a look at the linear transformation where you have a variable multiplied by 2, you are adding a constant to a variable. And don't also forget we have other kind of transformation. Okay, so going into what we're doing now. Okay, now instead of this can be argued out instead of using experience, because looking at experience may not be good in a may not be in a very good statistical standing. Why can't we use work history index instead of experience? Now take a look at the work history index. The work history index is experience minus 1 divided by 40, which is more or less like a linear transformation. Does that make sense? So instead of us to use experience, we can use a work history index. I know some of you may be, why do we have 40? Oh, maybe we're talking about 40 hours in a week, like people work, right? Get what I mean? Okay, on average. Now, and this may be argued out. How do we actually tell the world that replacing experience with a work history index, that we have not altered the relationship? I wanted to take a look at it too. When I'm using experience, look at what I have. When we use the work history index, we still have the same relationship. Can you see now? Except that the work history index, make more sense instead of using just experience. Okay, so I want to go into something else. This time around, I want to focus on elephants. There's a particular mama that we call elephants, and the research question here is when we have information about the body weight of elephants, can we predict the brain weight? Okay, we want to, and we actually have a lot of elephants. Okay, but when we plotted, um, the brain weight against the body weight, we found that African elephants and Asian elephants, they are acting like an outlier. If you look at what we are seeing right now, okay, and don't forget one of the assumptions of linear regression is that there should be absence, right, of outliers. Because if outlier is present and it's it's uh it's problem, it could be problematic to the model. Now it can be argued out if you if you ignore that and you decided to fit a linear regression, if you ignore the potential threats of the outlier, of course, you're basically going to have your beta naught to be 71.2, and the beta want to be that. Okay. Now, some researchers can argue this, that, okay, you know what? Of course, we don't expect this model to fit the data well because of the presence of outliers. The outliers in this case, of course, can be seen to be Asian elephant and African elephant. And some may want to argue this out, that, okay, let us remove them. Let's remove the two elephants. And after removing the two elephants, let us actually replot that. But after removing the two elephants, okay, this is what we have. That does not necessarily change the trajectory. At times, removing an outlier may not solve the problem. Okay, so what can we do? Okay, how can we tolerate the outlier in a data set without removing them? Okay, now, but we can actually achieve that through transformation. Okay, but I'm gonna show you this quickly. How do we know that the presence of these two elephants? How do we know that the presence of outlier will basically lead to violations? If we want to know, of course, you know what we always do. When you are trying to evaluate a model, when you're trying to look at the regression diagnostics, like we want to look at the residual plot. You know, remember the other time, the residual plot should not have a pattern, okay, for linearity assumption, okay, to hold. Now, this is a residual plot, okay, with, and now there's something new that I'm going to show you today. I've not been telling you how, what is a diagnostic plot to check for assumptions of normality. Let me tell you this. Residual plot can only, check for assumptions of linearity and constant variance. Residual plot cannot be used to check for assumptions of normality. And the diagnostic plot can be used to check the assumptions of normality is what we call a normal KQ plot. Okay, so the normal KQ plot, we for it to be normal, okay, we expect something like a diagonal straight line. But right now, what are you seeing? That's not a diagonal straight line. So what you're seeing here now is actually giving you an indication that so many assumptions are violated because of the presence of African elephant and the Asian elephant. As you can see, the residual plot actually has pattern, and of course, there's no constant variance in the residual plot. And if you look at the normal KQ plot, the normality assumption is violated. Okay, so we now want to propose now. There's a problem now, and you know what? We don't want to remove these outliers. We actually want to look for a way to transform the model in order for us to ignore, the potential threats posed by outliers. And because of that, we actually going to have what I call the trial and error method. Now, let me tell you this: we got different kind of transformation. We don't want to waste our time. How do we know the candidates of transformations that we basically going to consider? We're talking about weight. And Asian elephant and African elephant, they weight heavily compared to other elephant. Because of that, the data set is going to be skewed to the right. So what do we need to do to bring the data set to the center? When I say center, well, we're talking about normal distribution. Okay, give me 1 second. I'm gonna, the presence of outlier in a data set is going to skew the distribution of the data set either to the left or to the right. Okay, so if I have, uh, you know, if I have this right now, okay, and this is the center, right, and this is skewed to the right, okay. If data set are skewed to the right and I want to bring them back to the center, then I'm actually going to use a mathematical principle of compression. We're going to compress. What do we use in mathematics to compress our data? Square root, logarithm. When you take the square root of something, when you take a square root of 25, that gives you 5, right? It means you are compressing. It's too high, okay? Or when you take the log or something. And that was why, take a look at the transformation. We use the reciprocal. Number one is reciprocal. 1 divided by something is going to make it small. In the second one, we take the log. Log can also make it small. Then with the third one, we take the cube root. The fourth one, we take the square root. Okay. So the two variables involved. Okay, variable y, variable s, the brain weight, the body weight, we actually use the same transformation. And looking at this, what kind of transformation that work? Of course, the one that work is the log transformation, because the when you transform the relationship, we actually want to attain. What do we want? We want a straight line. Initially, it was not a straight line. How do we achieve a straight line? Which particular method technique achieve a straight line here is the log, the B part. Does that make sense? So if you want to actually transform the relationship, between variables, okay, or following violation, of course, you're basically going to try all of that, okay. And as you can see now, the logarithmic transformation actually work. Okay, so, and of course, I just justify. I said, why do I use the same transformation on X and Y? Because at times we could use a transformation for Y, maybe different from for S, but this time around, X and Y has the same unit, weight, brain weight, body weight. Does that make sense? That's why we use the same transformation. And which one do we choose? Of course, we choose the one in B. Okay, the one in B is actually what we choose, because with that actually brings our situation back to linearity. Okay, now let me tell you this. You know, when this guy has an headache, okay, and if this guy doesn't really take care of the headache, it could lead to other diseases. Now, and if this guy treats the headache, of course, he has succeeded in preventing any ugly situation. Do you know that the transformational effort now, okay, with linearity? Not only that, it's also going to solve the problem of normality. It's also going to solve other violations. And how do we check whether this transformational effort has, addressed other issues? I'm going to show you now. Take a look at what I want to show you now. I'm displaying two residual plots. The first one is before transformation. Do you see the way residual plots look like? The residual plot actually has pattern, but after transformation, after taking the log, look at that. Log of that on log of that, that was what I'm regressing now. What do you see after? The residual plot does not show pattern, which means when residual plot does not show pattern, that confirms that linearity assumption is attained. And not only that, look at the constant variance as well. Okay, what is the cardinal? If you want to do that, that is the cardinal. MOD2, maybe your MOD1 is the where you use the old variables. Okay, the MOD2 now, what is that? LM log of that on the log of that, using the data mama. If you want to have this plot in R, like how do we generate a residual plot in R? It's just going to be plot MOD comma 1. Just going to have the plot, residual plot. Now, you can take a look at that. What about the one for normality? Let's see. This is before the intervention. The normal QQ plot shows a violations of normality assumption. Then after transformation, don't forget, take a look at that. We haven't transformed. That was why you see LM, brain weight on body weight. But after transformation, using log, oh my God, what are you seeing now? That's a diagonal straight line indicating that the normality assumption now hold. Any question? You can see the transformational effort has fixed a lot of problems. Fixed linearity, it fixed constant variance, and also fixed normality. We have a way to check for all this. And that's why we're checking now. How do we know whether, okay, go ahead. Yeah, it's more or less, if you take a look at it too, the we actually want a diagonal straight line. This is looking more diagonal. So you know what I mean by diagonal straight line. The other one was horizontal. Horizontal is a bad one. Horizontal is trying to show the violations of normality. That's a good question. Okay. So that is what you need to, but you know what? We also, apart from using a graphical way, we also have a standard statistical test to test for the normality, which I call Shapiro Wiki test of normality, which I'm still going to walk you through in the future. Okay, so how do you get this in R? If you do that, you're going to do plot MOD comma 2. Plot MOD comma 2 in R will actually lead to we enable you to generate the normal QQ plot. So take a look at that. Now, why does the log transformation work for this study? Mathematically speaking, the log transformation actually work because the relationship initially was multiplicative. You know, when relationship is multiplicative, when you take the log, like the log of a product, what is it going to give? The log of a product is going to be the sum of the log in math. Okay, so that is why. So we trying to go back, and this is the relationship initially. The relationship was not supposed to be linear initially, and this is multiplicative in nature. Okay, the brain weight equal to the alpha multiplied by body weight raised to the power beta 1 multiplied by delta. If you take the log of this of both sides, you're going to have that. Take a look at that. You're going to have that in the hand. What are you going to have? Finally, this is a log. This is the reason why we're taking the log of this guy, taking the log of this guy, because initially, when you take a look at the origin, okay, the relationship was multiplicative in nature. Okay, so that was why it actually worked. Okay, so um, on the power transformation now, okay, of course, I walk you through different kinds of power transformation. You can say W raised to power lambda. We're trying to figure out the optimal values of lambda, and that is if lambda is not equal to 0. And if lambda equal to 0, of course, we're doing a logarithmic transformation. Now, what is the takeaway? The power transformation is very useful. Uh, the power transformation enable us to obtain linearity. When there's a violation of linearity, you can actually obtain that. It can stabilize on the covariance because initially, looking at the residual plot, there was a violation of a constant variance. And of course, using power transformation, we actually get that stabilized. Then we also obtain normality, okay? And that will enable us to also get rid of unusual observation. You can see now. We're actually modeling this without removing the unusual observation where, the transformation of a model is more or less like you are now using a robust method. Okay. A robust method. Okay. So, but let me tell you this, but not guaranteed to fix the problems. I'm going to tell you about this later. Okay. Because what if your variable values are negative? At times in measurements, depending on what you are measuring, and you have a negative value. Can I take the log of negative? That will be indeterminate, right? Okay. So in some situation where your variable is negative, that may not fix the problem. So what are we going to do in that kind of situation? Of course, we got some special models in statistics. We got series of nonlinear models in statistics that actually work. Okay. As time goes on, I'm actually going to walk you through all of that. Okay, I put some arrow code in case you want to copy this into R to just, this is on the mamas. Okay, the elephant that I just talked about. You need to copy all this, like install a package is called mass into R. And the moment you write the data, mamas, package equal to mass, you'll be able to have access to the data set. Okay. Now, here, if you want to, this is just a way to generate a scatter plot between the brain weights and the body weight. And of course, this is what you have. As you can see, there are 2 points that's actually deviated away, far away from others, right? The one I refer to, the African elephant and the Asian elephant. Okay, so this is a final. This is when we now take the log of the two variables. Okay, this is a code. If you follow other code, okay, you actually gonna you can see this is looking like a straight line. Okay, now when we have the log of the variables now and this attain linearity, of course, I showed you the other time how you can actually investigate whether the assumptions of constant variance, linearity using the residual plots. And of course, you can also investigate assumptions of normality using the normal QQ plot. Okay, so when you do the summary now that you have a log and log, let's say the output. Okay, I told you if I actually said that equal to that, and I said I put a summary, the summary of that is basically going to give me arrow output. I'll take a look at the arrow output now. So this is the arrow output now. You can see the log body, the log brain, and you can see the p-value associated with the intercept and slope or significant. Significant in the sense that the p-value associated with the intercept and slope is less than 0.05. If I want to know whether how significant is a regression parameter, how significant is more or less, testing whether it is zero or not. Okay, you're going to make use of the p-value. Okay, you compare the p-value with the level of significance. What is the standard level of significance we use? That's 0.05. When the p-value is less than 0.05, of course, we are actually going to conclude that that parameter is statistically significantly different from zero. Okay, so in case you want to plot the log, you want to plot, the other time we did predictions, right? Yesterday we did a prediction. You can, and the prediction, the type of prediction we did the one that has to do with the individual, right? And we did the one that has to do with the mean. You can also do the same here. Like, okay, I basically want to predict the brain weight of elephant, giving information about the body weight. Of course, what we are trying to tell you, if you want to make a prediction, you are going to use the one that involve the log. Does that make sense? Because the one with the log, okay, we have assumptions intact. If you don't use log, of course, if you you are not going to have any reasonable prediction. And that's what I'm trying to do. If you take a look at all this code now, it's about that. And that actually gave me this. Take a look at what I have now. Okay, so what you're seeing now is actually, take a look at, there are two lines that are far away. I'm going to award an extra credit now. Do you see two lines, solid line, far away? And you see another two lines very close to the one in the middle. The fitted line? Okay. Now I need someone for extra credit. The lines that are far away, the two lines that are deviated far away from the center, and the one that are close, what do they represent? Go ahead. The what? Okay, let me give you more clue. The information you are going to use now will be the one from yesterday. Yesterday, we talked about prediction interval for individual, right? We talked about confidence interval for mean prediction. Okay, out of the prediction interval and the confidence interval, which one has a wider range and which one has a narrow? Then you'll be able to answer this question. Now you go ahead. No, which means the one that is very close to the line is a confidence interval. The one that is far away is a prediction interval. Send me a message for extra credits. Does that make sense now? When you see the middle line, that thick one, the blue one, that is the line of the best fit, right? Now, we have other two line that is very close to that, right? Because when you are getting interval, you are getting two values, lower, upper, right? So the lower and the upper that is very close to the line of best fit, like for those of you online, I'm actually referring to this guy here is a line of best fit, and the other line, this line and the other line, okay, that is your confidence interval, which is the interval of the prediction, for the average. The one for the average will be very close to the line of best fit, but the one for the individual one is this guy and this guy, the one that is far away. And you know why that happened? Because the standard error associated with that of the mean is smaller compared to the one for individual. That was what so what I'm displaying now. This is the reason why in statistical analysis we normally we like talking about the mean, talking about the average. Okay, so we have other form of transformation that I actually call the Bosco transformation. The idea of the Bosco transformation, we want to figure out the lambda, okay, that will work, okay, and I have a data set given like this, okay, and I realize that this is not a straight line, and I want to determine, the other time we were assuming value for lambda by considering square root transformation, log transformation, this, if we want to save our time. And the Bosco transformation can give us the unique value for lambda instead of trying this, trying that, trying the square root, trying the log, trying all of that. We don't need all of that. That is why the Bosco transformation, we actually figure we can use it to figure out the optimal values of lambda that work. Now, the optimal values of lambda that work here is negative 0.42. Take a look at that. It is that negative 0.42 that we're going to remodel, because by Bosco transformation, the new variable is going to we have a y. The Bosco transformation will transform the variable y, the dependent, and it's going to be y raised to power lambda minus 1 divided by lambda. That now depends on the values of lambda, so that we need to figure out. Okay, so if you write that, we figure it out, we got the values of lambda to be that, then you now begin to run the regression, the new one, and in the end, when you run that, if you now want to investigate, take a look at the two. The first one, this is when there was a problem, there was a violations of normality. And after fixing the problem, you see what we have. Okay, so the essence of the Bosco transformation, let me tell you, the Bosco transformation will enable us to determine the optimal values of lambda that work. But we use Bosco transformation to transform the dependent variable, because in most of the time, whenever there's a problem, okay, maybe what we need to transform is a dependent, not independent. And that's exactly what we're doing here. That's what we're trying to do here. Okay, trying to write a Bosco to be able to get what is the optimal values of lambda. Take a look at that. And it is that optimal values of lambda that we go. You can see our new variable now is going to be y raised to power lambda minus 1 divided by lambda. That's what we're regressing. And why we've already found the lambda how. Okay, in the end, we actually using that, then we have our model. Okay, this is where I'm actually going to stop today. Is there any question on what we've done so far, whether in person or online? Is there any question? This is another, let me just make a summary of what we've done today. Today, I introduced you to transformation. Of course, the idea behind transformation is there's a problem. It's an intervention, and we basically want to see which intervention will work. Okay, I show you a series of transformation that we have. And finally, I also show you how you can use a Bosco to figure out the optimal values of lambda that is basically going to work. I walk you through example where we're trying to predict the brain weight of elephants or giving the body weight. And of course, we realize the presence of unusual observation, the African elephant and the Asian elephant. And when we decide to make a conclusion based on fitting linear regression on that is going to mislead. And of course, I demonstrated to you assumptions that were violated. We saw normality assumption violated. We look at the normal KK plot. We saw it was violated. We look at the residual plot. We saw that linearity assumption was violated. We saw that the constant variance assumption was violated. And we now try different kind of transformation. I remember we tried the log-log, the reciprocal transformation, the square root transformation, and the cubic transformation. We actually use all of that because the fact that the presence of the Asian and the African elephant, because they are very heavy, and that will skew the data to the distribution of the data to the right. And of course, we need a mathematical transformation technique that can compress the data. And that was why we actually use a square root. We compare, part of the transformation that we try was a square root transformation, the cubic, the reciprocal, and the quadratic one. And in the end, how do we know whether our intervention has worked? We can generate a scatter plot again to be able to see. We can actually generate a residual plot. We can look at the normal KK plot to be able to see whether the intervention worked. And finally, I also show you the Boscos transformation. The Boscos the idea of a Boscos is to transform the dependent variable. We're trying to look for the values of lambda that work. And when you follow the code that I show you, you can optimally, from your data set, you can determine the values of lambda that will work. Okay, and after determining the value, then we can run the regression again. And of course, whatever we get after that can be trusted. So that is what we did today. The only condition under which we can make an inference using a model, is when I can say somebody is talking, but the person is muted, except if that is not a background noise or in a way. But I can say somebody is talking, but is muted. For those of you that are online. Okay, so like I said, this is going to be the end of the second week, just like what I did in the end of the first week. I want you to send me a message, and this message is basically going to be getting a feedback from you. You need to rate your understanding of what we did this week, and you're going to rate that from 0 to 100%. And if what you have is less than 100%, I need you to include in the message what you want me to clarify. So like I said, we are moving gradually to the midterm. And let me tell you this, over the weekend, I'm actually going to release practice questions for the midterm. And of course, before the midterm, I'm actually going to dedicate a lecture, a class, to review, these practice questions, where I'm going to tell you what my expectation is when I give you a particular problem. Okay, in the absence of question, make sure you stay safe and make sure you attend the lab tomorrow. Of course, in the lab tomorrow, my TA is basically going to walk you through the practical demonstration of all what we've done over the week. And let me tell you this, when we give assignment, you're actually going to use the knowledge of the lab. And that is why you need to pay more attention when you attend the lab, as the lab is very, very crucial to this course. Make sure you stay safe and have a lovely week, lovely weekend, lovely day, lovely weekend. I'm going to see you on Monday. Bye for now. Thank you too. Thank you. Yep. You're welcome. Thank you too.